The manufacturing process at Hoffmann Propeller embodies a blend of tradition and innovation, rooted in the company's inception in 1955 in Rosenheim, Germany. Specializing in propeller technology, Hoffmann Propeller has evolved into a global player within the aviation industry, boasting trade relations in 80 countries. At the core of their craftsmanship lies an extensive pool of employee expertise. This knowledge base not only facilitates prompt handling of inquiries, but also fosters intimate connections with clients worldwide, driving a continuous cycle of product enhancement through daily improvements. Remarkably, despite technological advancements, Hauptmann propellers maintain their foundational material as premium wood. This choice signifies a commitment to craftsmanship, entailing a series of aligned production steps. These steps intricately handle wood as the primary natural resource, blending years of experience and comprehensive knowledge with modern CNC technology to ensure exceptional product quality. While significant aspects are handled using cutting-edge technology, pivotal details are crafted manually on spacious manufacturing floors. Precision and attention to detail define their manufacturing process, aiming for finesse to bring out intricacies and nuances. This approach extends to production steps, coating techniques, and a carefully sequenced functionality, guaranteeing propeller longevity even in the harshest weather and environmental conditions, adding to the joy of flying. Their expertise is further exemplified by their adeptness in using hand tools, employing sophisticated formulas, and maintaining strict tolerances in precise finishing. This hallmark craftsmanship extends to personalized services encompassing propeller handling, delivery, construction, refurbishment, and tailored solutions, all aimed at achieving perfection. Each finalized propeller undergoes exhaustive checks and meticulous documentation, ensuring precise execution and quality control. Collaboration with suppliers and extensive inventory management complement their commitment, integrating diverse testing methods, measurements, and control techniques to uphold stringent quality standards. Their product range not only includes various galvanic coating options, but also encompasses regulator overhauls from renowned manufacturers. This diversity defines their extensive delivery and service portfolio for propeller assemblies. Driven by experience, fairness, and forward-thinking strategies, their management is poised to anticipate and exceed the evolving expectations of their customers, perpetually aiming to realize the dream of flight. As a dedicated partner standing at the forefront, Hoffmann Propeller ensures a seamless journey towards achieving aerial dreams through their commitment to excellence and innovation. In Delaware, GE's Lean Lab advances CMC technology, transferring insights to North Carolina's Asheville plant, producing CMC shrouds for jet engines. In Huntsville, Alabama, SICK Materials support CMC manufacturing. GE established 9 U.S. factories, 4 for CMC, investing $450 million, creating 700-plus jobs since 2008. The F414 military engine incorporates advanced oxide-oxide ceramic matrix composites, CMCs, in critical components like the shrouds and combustor. These CMCs, composed of ceramic fibers in an oxide matrix, offer exceptional heat resistance, reducing cooling air needs. Their deployment in the F414 enables higher engine efficiency, increased durability, and improved performance under extreme temperatures, crucial for military aviation. The F136 military engine, developed by GE Aviation, showcased pioneering use of structural ceramic matrix composites, CMCs, in its high-pressure turbine shrouds. These CMC components, featuring silicon carbide fibers embedded in a silicon carbide matrix, demonstrated exceptional heat resistance and durability, setting a precedent for integrating CMCs in advanced jet engine designs for enhanced performance and efficiency in military aircraft. The CFM LEAP engine garnered 10,000-plus orders, with 18 ceramic matrix composite (CMC) shrouds per engine entering service in 2016. GE's Adaptive Cycle Engine, ACE, stands out for its innovative use of ceramic matrix composites, CMCs, across the hot section, achieving a remarkable 25% enhancement in fuel efficiency. The key to ACE's efficiency lies in its utilization of CMCs throughout critical components exposed to extreme temperatures. CMCs, specifically silicon carbide-based materials, are deployed strategically, providing exceptional heat resistance. These components endure temperatures approximately 150 degrees Fahrenheit higher than traditional engine materials. By employing CMCs in the hot section's core components, like shrouds, turbine blades, and combustion chambers, GE maximizes efficiency. The CMC's unique properties, including high durability and resistance to thermal stress, enable the engine to operate at elevated temperatures without compromising performance. The widespread use of CMCs also facilitates a significant reduction in cooling air requirements. Traditionally, engines required substantial cooling to maintain component durability. However, with CMC's ability to withstand extreme heat, less cooling air is needed. This surplus air is redirected into the engine's natural flow path, optimizing fuel efficiency and enhancing thrust. GE's innovation in incorporating CMCs into the ACE demonstrates a paradigm shift in engine design. The combination of these advanced materials allows for higher operating temperatures, resulting in increased engine efficiency and performance. Achieving a 25% improvement in fuel consumption signifies a monumental leap in aerospace technology, promising more sustainable and cost-effective aviation. The GE9X engine, powering the Boeing 777X, boasts a 10% improvement in fuel efficiency compared to its predecessor, the GE90. Incorporating advanced technologies like ceramic matrix composites, it delivers enhanced performance, reliability, and fuel economy for the next-generation aircraft. Between 2012 and 2020, ceramic matrix composite (CMC) production rates witnessed a staggering increase. Starting at 100 parts in 2012, the advancements in manufacturing capabilities propelled production to an impressive 32,000 parts by 2020. This exponential growth, a leap from modest figures to a significantly larger scale, indicates substantial advancements in technology, process optimization, and industrial scalability. The remarkable surge in CMC production reflects the industry's increasing confidence in these materials and their application across various sectors, particularly in aerospace, for their lightweight, high-strength, and high-temperature capabilities. In Alabama, GE established 2 new CMC manufacturing facilities with a $200 million investment, generating 300 jobs. Silicon carbide ceramic fiber plant produces materials for high-performance ceramic matrix composites, CMCs. CMC tape operation applies proprietary coatings to ceramic fibers for advanced composite manufacturing. The Asheville, North Carolina plant stands as the world's inaugural facility dedicated to mass-producing ceramic matrix composites, CMCs, marking a significant milestone in advanced manufacturing. With a remarkable $125 million investment, this pioneering establishment has revolutionized the industrial landscape, introducing cutting-edge techniques for large-scale CMC production. This groundbreaking initiative has not only propelled technological advancements, but has also fueled economic growth by creating 340 new jobs in the region. The plant's strategic location serves as a nucleus for innovation, attracting top-tier talent and fostering expertise in CMC manufacturing. By spearheading the mass production of CMCs, Asheville's facility plays a pivotal role in transforming industries reliant on high-performance materials, especially in aerospace and power generation. Its state-of-the-art infrastructure, coupled with extensive research and development efforts, positions it as a cornerstone in the realization of more efficient and durable components for various applications. The core stage of NASA's second Space Launch System (SLS) rocket, designed for the Artemis II mission, now proudly houses all 4 RS-25 engines, a crucial milestone accomplished by Aerojet Rocketdyne, a part of L3Harris Technologies. This assembly symbolizes a pivotal step towards propelling humans beyond the confines of low Earth orbit for the first time in over 50 years, a monumental mission eagerly awaited by the global space community. Among these engines, 2 are upgraded Space Shuttle main engines, SSMEs, that previously soared through space missions, while the remaining 2 are poised to make their inaugural journey aboard the Artemis II mission. Scheduled for liftoff in 2024, these 4 RS-25 engines will play a pivotal role in propelling NASA's Artemis II crew, comprising the first woman and a person of color, on a historic lunar orbit aboard the Orion spacecraft.
All right, Mac, hold her up.
Bill Muddle, the lead -25 rupees field engineer at Aerojet Rocketdyne, expressed satisfaction with the installation process, citing the incorporation of invaluable insights gleaned from the Artemis I mission. The RS-25 engines earmarked for the initial SLS rockets underwent upgrades, including the integration of new controllers and other enhancements, specifically tailored to facilitate deep space exploration. Notably, components from the historic Space Shuttle Columbia's maiden voyage, STS-1, feature in all 4 Artemis II engines. Engine 2047 and 2059 boasted an impressive combined record of 20 Space Shuttle missions, culminating in the final and penultimate flights of the shuttle program, respectively. Distinguishing themselves from the shuttle inventory, engines 2062 and 2063 stand as unique entities, having never ventured into space, albeit containing certain components from high and low pressure pumps and valves that had experienced space missions. These engines were crafted by Aerojet Rocketdyne, utilizing main components originally destined for the shuttle program, but were never launched, including the nozzles and main combustion chambers. Engine 2062 holds the distinction of being the final engine assembled for the shuttle program, while its counterpart, Engine 2063, was purpose-built for SLS, featuring the modern controller standard across all RS-25s. Both engines underwent rigorous ground testing at NASA Stennis. In the imminent future, the SLS core stage designated for Artemis II will undergo a battery of tests, electronic, pneumatic, and hydraulic, to ensure seamless integration. Upon completion, it will journey via NASA's Pegasus barge to the Kennedy Space Center in Florida, where preparations for launch will ensue. Looking ahead, future SLS missions beyond the 5th will be powered by newly manufactured RS-25 engines, projected to cost 30% less than their shuttle program predecessors. Aerojet Rocketdyne has already initiated construction on major components, employing cutting-edge manufacturing technologies to achieve the targeted cost efficiency. Each -25 rupees engine will undergo rigorous testing at NASA's Stennis Space Center before integration into an SLS flight, heralding a new era in space exploration, building upon the legacy of the esteemed SSMEs. The United Launch Alliance, ULA, rocket factory stands as a pinnacle of technological innovation and precision in rocket manufacturing. Spanning an immense 1.6 million square feet in Decatur, Alabama, this facility is the birthplace of rockets that soar into space, embarking on missions that span the solar system and serve critical national security, scientific exploration, weather observation, and communications satellite deployment. At the heart of this manufacturing marvel lies a synchronized symphony of intricate processes and cutting-edge technologies. The production commences with the transformation of large aluminum plates into designed patterns through a series of 4 double gantry skin milling machines. This initial step not only shapes the components, but also significantly reduces their weight by a staggering 70%, while preserving around 75% of the original material strength. Once the aluminum panels are machined, they undergo anodization to safeguard against corrosion, ensuring the durability and longevity of the components. This process involves a high-pressure wash followed by immersion in a series of chemicals, culminating in a sealing process vital for protection against environmental factors. The next stage involves the transformation of these panels into the essential barrel sections of the fuel tanks. This is achieved through precise bending and pressing in the brake form and bump press, creating the curved radius required for the fuel tank construction. The barrel sections are then subjected to friction stir welding, a distinctive process employing frictional heat and stirring of the parent material to form an exceptionally strong welded joint. Remarkably, this process doesn't utilize any filler material, contributing to the integrity and robustness of the final product. The assembly continues with the welding of domes onto each end of the barrel sections, thereby completing the initial stage fuel tanks. Rigorous pressure testing follows, affirming the structural soundness and integrity of the welds before the tanks progress to the next phase, spray-on foam insulation. In this booth, tanks receive a priming and insulation treatment that shields them from the extreme acoustics experienced during liftoff. Moving forward, these insulated tanks advance to final assembly, where additional components like wiring and engines are meticulously integrated. Notably, this factory doesn't only focus on first stage or booster production, it's also the site for the construction of ULA's second stages. The construction of Centaur's upper stages involves a delicate process using thin stainless steel structures, rendering it one of the most efficient upper stages in current use. The assembly of these stages involves welding together pie-shaped sheets to create the domes or bulkheads, followed by a combination of spot and seam welds to assemble the bulkheads and tank skins. Critical to the Centaur's functionality, the tanks receive their spray-on foam insulation to provide thermal protection for the cryogenic fuels they hold. These tanks, known as pressure-stabilized tanks, derive 90% of their weight from the fuel and oxidizer loaded pre-launch. Final assembly culminates with the installation of engines, avionics, pneumatic systems, and propulsion systems, marking the completion of an exhaustive journey where every system on both the booster and Centaur undergoes rigorous testing to ensure optimal performance. Once the rockets pass through testing and preparation, they exit the factory, rolling about a mile down the road to the Tennessee River's dock. Here, they're loaded onto ULA's specialized cargo boat, the RS rocket ship, embarking on an 8-day journey to Cape Canaveral Space Force Station in Florida or a 23-day trip to Vandenberg Space Force Base in California. Commencing the manufacturing journey is the hub, the pivotal center to which the propeller blades affix. Initially shaped by forging, it undergoes intricate machining in a computer-guided mill, sculpting it into the requisite form. Once machined, the hub is primed for integration with the engine. Moving to the blades, their initial rough shape undergoes refinement through precision machining in a lathe. A thorough cleansing with a liquid lubricant clears away metal shavings, preventing the generation of heat due to friction. This process intricately shapes the shank, enabling it to fit seamlessly into the hub. Further perfecting the blade's form involves manual finishing, employing rotary and belt sanders to erase machining marks. A polishing wheel brings out the luster of the metal, followed by a rigorous cleansing to eliminate any residual dirt, oil, or grease. The subsequent treatment involves immersing the blades in a bath of water and chromic acid, sealing the metal's pores to avert corrosion. Rigorous quality control measures include subjecting critical parts to scrutiny for surface defects using a fluorescent solution. Inspection under a blacklight distinguishes approved parts with a reassuring blue glow, while any imperfections illuminate as vivid fluorescent green, leading to the repair or rejection of defective parts. Approved blades progress to the paint shop where a black coating is applied on the rear side to prevent glare for the pilot. Safety stripes are added for enhanced visibility while the propeller is in motion. A resilient rubber encasement housing an electric heating element, known as a de-icing boot, is installed to prevent ice buildup, adaptable to the blade's curvature. Lubricating a specific section of the blade shank precedes the installation of a robust steel ball bearing system, securing the blade within the hub while facilitating pivotal movement to alter angles. The blade shanks integrate into a steel fork, ensuring uniform angles for all blades. A pivotal component, the pitch change rod, responsible for adjusting blade angles, enters the assembly process. Engine oil's hydraulic pressure propels a piston within the rod, maneuvering the blades to the desired angle. Following precise positioning, sealant application on the hub precedes its fusion with the bottom half housing the ball bearing set. Rubber seals and a robust spring furnish essential counterpressure. Finally, the piston and pitch change rod securely fasten onto the fork, guaranteeing a leak-proof assembly. The cylinder enclosing engine oil is hermetically sealed, culminating in the completion of the propeller assembly. The result of this meticulous process is an impeccably crafted airplane propeller, fully prepared for use. The GE9X boasts 16 fourth-generation carbon fiber composite fan blades, thinner, stronger, and more efficient than previous models. It integrates a compressor with a record-setting pressure ratio of 27:1, marking the highest in aviation history. The engine incorporates a next-gen lean-burning combustor capable of handling extreme pressures and temperatures. Advanced manufacturing techniques like 3D printing are utilized, enabling the creation of previously impossible components. The use of cutting-edge materials, including ceramic matrix composites, significantly enhances strength while reducing weight. This next-gen engine promises a 10% improvement in fuel efficiency compared to its predecessor, while keeping noise and NOx emissions well below regulatory standards. The GE9X assures the reliability expected from GE, aiming to power Boeing's 777X, representing a new era in aviation. Explore the GE9X engine's intricate technologies, such as the fan, compressor, combustor, and materials, emphasizing how these advancements contribute to its exceptional fuel efficiency. It also promotes GE Aviation's role as a global leader in providing engines, components, and integrated systems for various aviation applications, demonstrating their commitment to advancing aviation technology. The journey commenced in 2001 when StandardAero ventured into the realm of CF34 engine support, marking the genesis of a commitment to unparalleled service and engineering prowess. This milestone didn't just signify a milestone for the company, it was a pivotal moment for the aviation industry as a whole. From that point forward, StandardAero set a new standard, intertwining innovation, reliability, and customer-centric solutions into the fabric of its operations. What sets StandardAero apart is not solely its accreditation as the GE-authorized CF34 service provider, but also its multifaceted role as an independent MRO provider and a GE-designated fulfillment center. This trifecta of distinction speaks volumes about the trust and confidence vested in StandardAero by both GE and fleet leaders across the globe. The significance of entrusting CFM56-7B engines to an MRO facility licensed by GE cannot be overstated. It's not merely about repairing or overhauling an engine. It's about safeguarding an invaluable asset critical to aviation operations. Choosing StandardAero as the custodian of these engines offers more than just peace of mind. It's an assurance of expertise, precision, and unwavering dedication. StandardAero's approach to MRO for CF34 and CFM56-7B engines is comprehensive and meticulous. It encompasses a fusion of cutting-edge technology, a cadre of highly skilled engineers and technicians, and a commitment to adherence to the most stringent quality standards. Every facet of the maintenance and repair process is orchestrated with precision, leveraging the latest advancements in engineering and diagnostics. The CFM56-5B turbofan engine, a trusted powerhouse within the Airbus A320 family, serves as the propulsive heart of these aircraft, driving them forward through production of thrust. The fundamental principle behind its functionality lies in the generation of force or thrust by accelerating air between the front and rear of the engine. This process initiates with the large fan positioned at the engine's forefront. Acting as a colossal propeller, the fan propels air at a high rate, setting the stage for the subsequent components within the CFM56-5B to come into play. Let's break down the engine's anatomy. The CFM56-5B comprises several key components. Fan. This large diameter propeller kickstarts the airflow within the engine. Low and high pressure compressors. With a total of 13 stages, these compressors incrementally elevate the air pressure as it traverses through them. Combustion chamber. Here, jet fuel mixes with compressed air and undergoes combustion, intensifying the temperature. High and low pressure turbines. These turbines are responsible for reducing the pressure of the hot gas post-combustion. There are 5 turbine stages, 1 high pressure and 4 low pressure. Exhaust assembly. The final stage where the accumulated energy is expelled, propelling the aircraft forward. The CFM56-5B is categorized as a high bypass ratio engine. distinguishing between primary and secondary airflows. Approximately 80% of the air accelerated by the fan passes through the bypass duct, contributing 80% of the engine's thrust. The remaining airflow travels through the compressors, combustion chamber, and turbines before joining the exhaust flow. The operational sequence is as follows. The air undergoes compression in the compressors, escalating its temperature significantly. Upon entering the combustion chamber, fuel injection and ignition ensue, elevating the temperature further to a blazing 1,700 degrees Celsius. This heightened energy is then harnessed across the 5 turbine stages, strategically positioned post-combustion. As the air passes through these turbines, its pressure drops, driving their rotation. The turbines, nested concentrically within each other, in turn, drive the fan and compressors. Jet engines, particularly turbofans like the CFM56 and its successor, the LEAP, operate on a fascinating interplay of forces and engineering. These engines aren't just machinery, they're complex symphonies of air compression, combustion, and thrust generation. The turbofan's primary goal revolves around manipulating air to produce thrust, enabling aircraft to take flight. It begins with the fan blades, suctioning and accelerating air. This air compression and acceleration generate the necessary thrust for flight. 3D woven carbon fiber composites involve intricately weaving carbon fibers in 3 dimensions, creating a stronger, more durable material, ideal for aerospace, automotive, and high-performance applications due to enhanced structural integrity. Designed with 4th-generation 3D aerodynamics, the technology employs advanced computational models to optimize airflow, enhancing efficiency, stability, and performance in aviation and automotive industries. A kerosene particle within a jet engine's combustion process is a minute droplet of the fuel finely dispersed in the compressed air. During combustion, these particles mix with air, forming a homogeneous blend that ignites efficiently. With fewer particles needed in modern engines like the LEAP, their meticulous mixing with air before entering the combustor reduces peak temperatures, leading to enhanced fuel efficiency and minimized emissions, contributing to a more environmentally friendly operation. Advanced cooling systems within ceramic matrix composites, CMCs, are pivotal for prolonged service life in extreme conditions. CMCs, featuring ceramics reinforced with fibers, withstand high temperatures. The cooling systems utilize intricate designs, like internal air channels, to dissipate heat effectively. This prevents thermal stress buildup, preserving structural integrity. These innovations enable CMCs to endure harsh environments in aerospace and gas turbine applications, ensuring prolonged operational efficiency and durability. The industrial gas turbines from MAN Diesel and Turbo, particularly the MGT series, exemplify cutting-edge technology and engineering excellence. These turbines, developed at the Overhaul site, cater to a power range of 7 to 13 megawatts. Specifically, let's delve into the working principle of the MGT 6200 and MGT 6100, highlighting their distinct features and functionalities. The MGT 6200, a twin-shaft model, serves as a mechanical drive for applications like compressors. It comprises a gas generator with a high-pressure turbine on one side and a power or low-pressure turbine on the other, operating independently due to the presence of a second shaft. An electric motor kick-starts the gas turbine, initiating the high-pressure turbine's rotation, which subsequently drives the 11-stage axial compressor. The compressed air required for combustion is obtained through this compressor. Subsequently, within the 6 combustion chambers, the air is mixed with fuel gas and ignited. leading to the expansion of hot exhaust gases. These gases propel both the high and low pressure turbines, driving the respective shafts. The process begins with the axial compressor's blades striking and conducting air into the turbine while compressing it, resulting in a flow passing through the air intake casing. The air experiences a substantial pressure increase, 15 bars, before entering the combustion chambers, where the fuel-gas-air mixture is pre-mixed uniformly, promoting efficient combustion with significantly low emissions. Post-ignition, the expansion of the fuel-gas-air mixture due to combustion heat occurs, leading to its high-speed flow through turbine blades, subsequently driving both shafts. The exhaust gases at temperatures around 460 degrees Celsius pass through a diffuser into the outlet casing, where their residual heat can potentially be harnessed, for instance, to generate steam. Conversely, the MGT 6100, a single shaft model optimized for power generation, operates at a constant speed to drive an electric generator, sharing several assembly parts with the MGT 6200, including combustion chambers and the axial compressor. The MGT 6100 features a single continuous shaft, reducing the number of components by approximately 27%, comprising 7,846 individual parts, compared to the MGT 6200's 10,011 parts. Crafting the main gearbox bevel gear vertical shaft for Super Puma and EC 225 involves forging raw metal into blanks, precision turning them to specified dimensions, cutting gear teeth with exactitude, and employing specialized treatments like nitriding for hardness. Rigorous inspections, including ultrasonic, radiographic, and magnetic particle testing, guarantee structural integrity before assembly and rigorous testing. Let's delve into the steps of this complex manufacturing journey. Forged blanks, raw metal heated, shaped for subsequent machining processes. Turning, blanks machined using lathes to achieve precise shape dimensions. Gear cutting, intricate gear patterns precisely carved into shaft for optimal functionality and engagement. Nitriding, treating metal surface with nitrogen to enhance hardness, wear resistance, and corrosion protection properties. Spiral bevel gear grinding, utilizing specialized grinding techniques to ensure precise tooth profiles, enabling smooth engagement and optimal gearbox functionality. Electron beam welding, high-precision fusion of components using electron beams, ensuring strong, seamless joins without compromising material properties or structural integrity. Ultrasonic test, non-destructive inspection using high-frequency sound waves to detect internal flaws, ensuring structural integrity without damaging the component. Radiographic testing involves exposing the gear shaft to X-rays or gamma rays to reveal internal flaws, voids, or irregularities. The resulting radiographic images allow for precise evaluation of the component's integrity, ensuring any potential defects are identified and addressed before assembly. Knit water, a quenching and tempering process utilizing a nitrogen-based medium to enhance material properties and structural strength. Magnetic particle inspection, magnetizing the shaft and applying iron particles to detect surface flaws or discontinuities for quality assessment and assurance. Superfinishing, an abrasive machining process to achieve exceptionally smooth surfaces, reducing friction and wear while enhancing performance and longevity. Runout inspection, verifying rotational axis alignment for concentricity and precision. Surface roughness inspection, evaluating texture quality to ensure specified smoothness requirements are met. The 3D measuring machine employs advanced technology to precisely capture the shaft's dimensional accuracy and geometry. Using laser or optical sensors, it meticulously assesses every contour, angle, and dimension, ensuring compliance with exact specifications and allowing for detailed analysis and verification of the part's integrity before assembly. Gearbox assembly integrates meticulously crafted components into a cohesive unit. Following precise procedures and quality checks, each part, including the bevel gear vertical shaft, is assembled for optimal functionality. Rig testing simulates operational conditions, subjecting the gearbox to various stressors, temperatures, and loads. This exhaustive examination verifies performance, durability, and safety, ensuring the gearbox meets stringent operational standards and requirements. The main rotor hub assembly is pivotal, linking the gearbox to the rotor system. It integrates critical components like the bevel gear vertical shaft, ensuring the transfer of power and rotational motion to the main rotor blades. This assembly demands precision and reliability for safe and efficient helicopter operation. In the realm of energy infrastructure, few tasks carry as much complexity and significance as the installation or replacement of heavy machinery, such as gas turbines, at sites managed by entities like the General Electricity Company of Libya, GECOL. The endeavor to replace a gas turbine, weighing a formidable 38 tons, within a GECOL site in Tripoli, Libya, in December 2023, likely symbolizes a critical upgrade or maintenance effort aimed at bolstering the region's power generation capabilities. Libya, endowed with substantial oil and gas resources, has invested extensively in its energy infrastructure, particularly within its capital, Tripoli. GECOL, responsible for the generation, transmission, and distribution of electricity across Libya, operates numerous power plants and facilities across the country, serving the needs of both urban centers and rural areas. Prior to the installation phase, a comprehensive assessment and preparation period would have occurred. Engineers, project managers, and technicians would have evaluated the existing infrastructure, drafted detailed plans, and ensured all necessary resources, both human and mechanical, were at the ready. Handling a 38-ton gas turbine demands specialized lifting equipment and a skilled team adept at intricate maneuvering. Cranes with immense lifting capacities, hoists, and other heavy machinery would have been brought in to facilitate the delicate extraction of the old turbine and the careful installation of the new one. Each step in this process requires precision and adherence to stringent safety protocols to prevent any mishaps or damage to the equipment or the site itself. Furthermore, logistical considerations play a pivotal role, coordinating the delivery of the new turbine, ensuring its compatibility with existing infrastructure, and managing the removal of the old equipment all necessitate a synchronized effort. Timing, transportation, and contingency plans would have been devised to minimize downtime and disruptions to the power supply. The significance of this operation extends beyond the mere act of replacing a machine. Upgrading a gas turbine likely represents a commitment to enhancing energy efficiency, increasing power output, or ensuring the reliability of electricity supply in Tripoli and its surrounding areas. Improved technology in the new turbine could potentially lead to more efficient energy production, reduced emissions, and a more sustainable power generation process. Moreover, such endeavors often signify a country's dedication to modernizing its infrastructure, attracting investment, and bolstering economic development. Stable and reliable electricity supply is vital for industries, hospitals, homes, and overall societal progress. The smelting and forging of the perlitic steel, specifically the 15x2 grade, marks the foundational phase of WED 1200 reactor vessel manufacturing. This high-grade steel undergoes a process where massive ingots, weighing up to a staggering 360 tons, are carefully formed. The smelting involves precise temperature control and alloy composition to ensure the desired material properties are achieved. The forging stage employs immense press power, reaching up to 15,000 tons force. This incredible force is harnessed to shape and mold the molten steel into robust and precisely engineered components that form the backbone of the reactor vessel, ensuring unparalleled strength and resilience in its structural integrity. The bottom head forming involves a double-action forming press exerting a tonnage exceeding 15,000 tons, crucial in shaping the lower part of the vessel with precision and strength. Mechanical treatment and plating refine the components, employing specific techniques to enhance durability, resistance to corrosion, and overall performance, ensuring the vessel's longevity and reliability in operation. Mechanical treatment includes machining, polishing, and stress-relieving methods. Plating enhances corrosion resistance through coatings or surface treatments. Assembling and welding merge the fabricated components, meticulously aligning and joining the parts to create a unified structure. Skilled welding techniques like TIG or submerged arc welding ensure strong, leak-free seams crucial for the vessel's integrity and safety. Heat treatment at around 650 degrees Celsius optimizes material properties, enhancing strength and relieving residual stresses for durability. X-ray control conducts non-destructive tests, scanning for potential defects like three-dimensional anomalies, cracks, metal burnout, sponginess, or inhomogeneity within the reactor vessel. This comprehensive examination ensures the vessel's structural integrity and identifies any imperfections critical to its safety and performance. Hydraulic pressure tests scrutinize the integrity of pressurized equipment like the reactor vessel. Conducted with water, these tests simulate operational conditions by subjecting the vessel to extreme pressures. Instruments measure the generated pressure, reaching significant levels, such as 245 atmospheres. The vessel undergoes this test without any signs of rupture or leakage, showcasing its robustness under extreme conditions. These tests are crucial in affirming the vessel's capability to withstand operational pressures, ensuring it operates safely within expected parameters without compromising its structural integrity or safety standards. Once the site is deemed suitable, the RPV is transported to the facility under controlled conditions, often utilizing specialized transport mechanisms designed to handle its massive size and weight. Cranes and lifting equipment are strategically positioned around the installation site. The actual installation involves carefully lowering the RPV into its designated location within the containment building. This task demands absolute precision, as the vessel must align perfectly with connecting systems, such as coolant pipes and control mechanisms. Post-installation comprehensive testing and checks are performed to verify the RPV's functionality, integrity, and ability to withstand operational pressures and conditions. This includes pressure tests, leak checks, and verification of all safety features. The geological landscape surrounding Taishan Unit 1's nuclear island features stable terrain with a robust foundation, ensuring a secure base for the plant's critical infrastructure and reactor facilities. On October 26, the initial concreting for Taishan Unit 1's nuclear island marked the foundational start of critical construction efforts. The large-volume integral pouring technique ensured continuous cohesive concrete placement for structural robustness and stability. On October 23, 2011, the dome for Unit 1's nuclear island was lifted and precisely positioned. Pre-stressing tension involves applying forces to materials, like steel tendons, prior to loading to enhance structural strength, counteract potential stresses, and improve the overall stability and durability of the construction. On June 3, 2012, the reactor pressure vessel for Unit 1 was lifted and precisely positioned into place. The 3D measurement technique ensures precision in component alignment, while primary loop auto welding maintains quality and structural integrity seamlessly. On September 19, 2012, the inaugural steam generator for Unit 1 was installed accurately. On December 26, 2012, completion of primary loop welding fortified Unit 1's nuclear island structure. On December 4, 2013, the core catcher was installed, followed by the medium-pressure safety injection tank discharge on December 20, 2013, facilitating Unit 1's nuclear circuit cleaning. The construction of Unit 2's nuclear island paralleled Unit 1's, featuring a robust foundation and stable geological landscape, from initial concreting in October 2010 to the positioning of the dome in November 2011. Each step mirrored Unit 1's timeline, ensuring structural integrity and adherence to safety protocols. On September 12, 2012, Unit 2's nuclear island saw the precise lifting and placement of its dome. Manufacturing culminated on December 19, 2013, with the completion of 4 steam generators. Subsequently, on October 22, 2014, the reactor pressure vessel arrived, and on October 30, 2014, it was meticulously lifted and installed, marking a pivotal construction phase for Unit 2's nuclear infrastructure. On March 29, 2014, the closure of 4 cylinders for Unit 1's turbine was successfully completed, while on August 26, 2013, manufacturing of Unit 1's generator stator concluded, marking key milestones in the plant's turbine and generator assembly. On July 31, 2014, the completion of the seabed tunnel marked a significant achievement in infrastructure. Simultaneously, the construction of vital components such as the water intake channel, pumping station, drainage culvert, and underground gallery reinforced the plant's foundational support systems. The startup of the first EPR reactor commenced with testing phases. The cold functional test, confirming systems readiness without nuclear reactions, was successfully completed. Subsequently, the hot functional test, validating operational functionality with nuclear heat, concluded satisfactorily. The arrival of nuclear fuel on site signaled a crucial phase, followed by the receiving and loading of fuel assemblies into the reactor core. The culmination came with the completion of fuel loading, a crucial step before the reactor could begin its operational phase, marking a pivotal milestone in the reactor's commissioning process. In vacuum interrupter manufacturing, High-quality materials are shaped, cleaned, and sealed to create reliable electrical insulation and switching components. In the production of contact systems, specialized manufacturing techniques are employed to craft components with precise geometries and material compositions, ensuring optimal conductivity and durability within the circuit breaker assembly. Parts undergo thorough washing to remove contaminants before assembly. Components are assembled in a controlled cleanroom environment to prevent contamination and ensure product integrity and reliability. One-shot vacuum sealing braze ensures hermetic sealing for long-term reliability. Quality testing verifies functionality and reliability to ensure optimal performance. Vacuum level check ensures optimal vacuum pressure for interrupter performance. During internal resistance check, dielectric testing, the interrupter's internal resistance is measured and dielectric strength is verified, ensuring it withstands high voltage conditions and operates reliably. Components are integrated to assemble the circuit breaker unit. Circuit breaker undergoes rigorous testing to ensure reliability and performance standards. Mechanical operating test verifies smooth operation and functionality of components. Dielectric testing verifies the circuit breaker's insulation integrity under high voltage. Generator switchgear assembly involves integrating components to ensure efficient control and protection of electrical circuits within the power generation system. Routine testing involves subjecting the generator switchgear to simulated operating conditions to verify functionality, reliability, and adherence to performance standards. The production of a generator at Siemens Energy's Competence Center for Energy Transition Technologies is a process that involves state-of-the-art technology. From the initial stages of processing the core to the final quality checks before delivery, every step is carefully executed to ensure the highest standards of quality and performance. The process begins with the processing of the core, the essential component that converts mechanical energy into electrical energy. At the ergonomically designed winding stations, conductors are inserted and soldered by skilled workers. Each solder joint is inspected using ultrasound to guarantee its integrity. Once the core is prepared, it undergoes further development, insulation, and assembly of various components. Siemens Energy's strength lies in its ability to manage multiple production and development steps simultaneously, thanks to its spacious production halls and advanced machinery. One notable aspect of the production process is the creation of the stator housing. Layers of steel sheets are stacked on top of each other and welded to form a sturdy housing for the generator. This process requires precision and attention to detail to ensure the structural integrity of the final product. Another critical component of the generator is the rotor, which undergoes several machining steps to receive its mechanical covering. Quality control checks are conducted at each stage to verify cleanliness, completeness, and dimensional accuracy. Once all components are assembled, the generator undergoes rigorous testing to ensure its performance and durability. Siemens Energy's Advanced Technical Monitoring Area allows engineers to observe and control the testing process, ensuring that each generator meets the company's strict standards. After passing the testing phase, the generator is ready for delivery to the customer. Siemens Energy's unique logistics setup in Mulheim, with direct access to the river, facilitates the transportation of large machines to customers worldwide.
The ambitious task of delivering a staggering 120,000 units of 1B generators proved to be a logistical challenge that demanded innovative solutions. The sheer weight of these generators mandated a departure from conventional transportation methods. Thus, a specialized 9-axle truck trailer was enlisted to undertake the monumental task. With each generator possessing substantial weight, disassembling was not just an option, but a necessity to facilitate the unloading process. The intricate nature of the generators required a meticulous approach to separation, involving the careful detachment of the rotor from the stator. This procedure was executed with the utmost precision, considering the intricacies of the internal components and the need to maintain their integrity during transport. Executing this feat required a harmonious symphony of engineering and machinery. The extraction of the rotor from the stator was orchestrated with the involvement of 2 cranes. These cranes were positioned strategically to delicately lift and manipulate the separated components. The synchronization of their movements was akin to a choreographed dance, with operators communicating intricately to ensure flawless execution. The rotor, being the more sensitive of the components, necessitated an exceptionally gentle touch during its extraction. Once successfully extracted, the rotor embarked on the next phase of its journey. It was carefully transferred to a provisional storage site, a designated area meticulously prepared to accommodate these colossal components. The storage site was equipped with state-of-the-art facilities to safeguard the rotor's condition, shielding it from the elements and any potential damage. The Wasquatine Generating Station reached a significant milestone on November 14, 2011, as the final turbine runner was successfully hoisted into position. This monumental achievement marked the culmination of the Unit 2 turbine assembly, a crucial step in the project's advancement. The remarkable runner, weighing an impressive 150 tons, underscores the magnitude of this undertaking. The project's progression has been impressive, with a shift from the initial heavy construction phases involving rebar, formwork, and concrete, to the current focus on intricate electrical, mechanical, and turbine-related installations. This transition to more precise and delicate work highlights the intricate nature of assembling such a massive and complex system. A pivotal moment in the process occurred recently, as the team executed their most substantial lift within the powerhouse. This maneuver involved relocating one of the rotors into storage, enabling a shift in the assembly process. This creative solution was a response to challenges encountered at the project's outset, underscoring the flexibility and ingenuity of the contracting team. As with any substantial endeavor, unique challenges surfaced during the Wasquatine Generating Station project. However, the resolve of the team to surmount these hurdles and maintain the project's timeline has been unwavering. Minor complications emerged periodically, but were efficiently addressed to ensure the smooth continuation of the work. The process of overhauling a Whitehorse hydro generator is a meticulous endeavor that ensures the continued efficiency and reliability of Yukon Energy's power generation infrastructure. In the summer of 2013, an ambitious 10-year overhaul was undertaken on one of the Whitehorse units, offering a behind-the-scenes glimpse into the intricate operations involved. The overhaul kicked off with a comprehensive assessment of the generator's components and systems. Engineers and technicians meticulously inspected the unit, identifying areas that required attention. This initial step laid the foundation for a detailed plan that would guide the entire process. Disassembly came next, as the generator was carefully taken apart to its core components. This step demanded precision and expertise, as each piece was methodically detached and documented. Bolts were unscrewed, wiring was unlinked, and bearings were delicately removed. Every component was tagged and cataloged, ensuring a systematic reassembly later. With the generator disassembled, the focus shifted to refurbishment and replacement. Worn-out components were meticulously restored or exchanged for new ones. Bearings, seals, and gaskets were replaced to ensure optimal performance. Technological advancements were also integrated where applicable, enhancing the generator's efficiency and longevity. The heart of the overhaul lay in reconditioning. Components such as rotors and stators underwent meticulous cleaning and repair processes. Cutting-edge diagnostic tools were employed to assess the integrity of the parts and ensure they met the highest standards. Rewinding of the stator coils was executed with precision, a task demanding both skill and patience. After months of refurbishment, the reassembly phase began. This was a true test of the team's precision and expertise. With the assistance of detailed documentation and thorough quality checks, the generator started to take shape once again. Bolts were tightened with exact torque, and wiring was connected according to meticulous diagrams. In the realm of large-scale industrial operations, the intricacies of machinery maintenance and repair take on a monumental dimension. A remarkable example of this can be witnessed in the delicate process of removing a rotor from a colossal 32 megawatts generator weighing a staggering 127,000 pounds. The task at hand is no trifling matter. The rotor, an essential component within the generator, weighs over 45,000 pounds and demands a mere 3/4 clearance in radial space for a successful extraction. This feat requires not only technical prowess, but a fusion of innovation and experience. Enter the stage, a custom 20-foot steel tube, boasting a robust 1-inch wall thickness and a formidable weight of 3,300 pounds. This engineered masterpiece serves as a conduit for the rotor's journey. Its unwavering strength and tailored design facilitate the intricate maneuvering required for the extraction. To assist in this laborious endeavor, 2 colossal 50-ton cranes stand as sentinels. These mechanical giants are harnessed to gently hoist the steel tube and its precious cargo. The interplay of machinery and manpower transforms the workshop into a theater of controlled power and precision. With the cranes synchronized, the rotor's ethereal ascent begins, each inch of movement a testament to the dedication of the Smith Services team. The synchronization of effort, technology, and human skill harmonizes to manifest the rotor's detachment. This spectacle encapsulates the embodiment of engineering marvels and professional expertise. The generator, once a hub of energy production, now rests in dignified repose, awaiting meticulous inspection and repair. In the crucible of industrial maintenance, where mammoth machines silently weave the tapestry of modern life, the removal of a rotor emerges as an emblematic display of human ingenuity. The Smith Services team, armed with their custom steel tube and titanic cranes, epitomizes the fusion of craftsmanship and engineering, underscoring the remarkable heights that can be scaled when precision and innovation dance in synchrony. In the heart of Von Electric's state-of-the-art facility, a remarkable feat of engineering was about to unfold. A 1,500-horsepower motor, worn down by years of relentless operation, awaited its rejuvenation. Recognizing the importance of showcasing their expertise to clients and enthusiasts alike, Von Electric embarked on a 6-day motor rebuild journey that would not only restore the machine's vitality, but also capture the intricate process in a captivating time-lapse. Day 1. Disassembly and assessment. The process commenced with meticulous disassembly, as skilled technicians wearing protective gear dismantled the mammoth motor. Each part was carefully labeled and documented to ensure a seamless reassembly. The initial assessment revealed a worn-out bearing assembly, signs of overheating, and some degradation in the insulation system, all of which were expected due to the intense workload the motor had endured. Day 2. Cleaning and preparation. A significant portion of Day 2 was dedicated to thorough cleaning. Technicians employed specialized tools and solvents to meticulously remove grime, grease, and debris accumulated over the motor's operational lifetime. The parts shone anew, ready for the forthcoming restoration. Meanwhile, the team meticulously inspected each component, identifying which ones could be refurbished and which required replacement. Day 3. Component restoration and replacement. With a comprehensive list of components requiring restoration or replacement, Von Electric's well-stocked inventory came into play. Worn-out bearings were swapped for precision-engineered replacements, and damaged insulation was meticulously replaced, ensuring the motor's reliability and safety. As skilled hands worked in harmony, the motor began to resemble its former glory. Day 4. Precision reassembly begins. Day 4 marked the pivotal phase of precision reassembly. Armed with the knowledge of each part's placement and role, technicians gingerly began the process of restoring the motor's intricate internal structure. This step was a delicate dance of aligning parts, torquing bolts to precise specifications, and re-establishing the motor's core functionality. It was during this stage that the true expertise of Vaughan Electric's technicians shone, as their years of experience culminated in the harmonious reconstruction of the mechanical puzzle. Day 5. Finishing touches and performance optimization. As the motor's physical form neared completion, the focus shifted to the finer details that make all the difference. Electrical connections were re-established with utmost precision, and control systems were rigorously tested to ensure seamless integration. A round of initial tests was conducted to gauge the motor's baseline performance, providing a foundation for subsequent optimization. Day 6. Testing, tuning, and triumphant revival. The culmination of 6 days of relentless effort arrived. As the rebuilt motor roared to life, with bated breath, the technicians monitored various parameters to ensure the motor operated within optimal ranges. Adjustments were made, and the motor underwent a series of load tests to validate its restored power and efficiency. As the motor settled into its rhythm, it was evident that Vaughan Electric's meticulous approach had paid off. The beast was revived with a newfound vigor. Day 6. Testing, tuning, and triumphant revival. Throughout the 6-day journey, cameras strategically positioned around the workshop meticulously documented every twist of a wrench, every soldered connection, and every diagnostic reading. The resulting time-lapse encapsulated the transformation from a disassembled heap to a fully operational powerhouse. This visual chronicle not only showcased Vaughan Electric's technical prowess, but also highlighted their commitment to excellence, innovation, and client satisfaction. Vaughan Electric's 6-day motor rebuild time-lapse encapsulated the remarkable journey of restoring a 1,500-horsepower motor to its former glory. From the initial disassembly and assessment to the meticulous cleaning, restoration, and precision reassembly, the process showcased the intricate dance of technical expertise and precision engineering. The time-lapse not only serves as a testament to Vaughan Electric's capabilities, but also as an educational tool, offering a glimpse into the world of industrial motor rehabilitation. As the motor roared back to life, it not only marked a triumphant revival, but also a testament to the power of human skill and innovation. An oil lubrication bearing assembly is a vital component in various machines and mechanical systems, serving the essential function of reducing friction between moving parts while facilitating smooth rotational motion. This assembly consists of several integral components designed to work harmoniously and ensure the longevity and efficiency of the machinery it supports. At the heart of an oil lubrication bearing assembly is the bearing itself. Bearings are precision-engineered components that allow relative motion between two parts while minimizing friction and wear. In oil-lubricated systems, a layer of lubricating oil is introduced between the rotating and stationary parts of the bearing. This oil forms a thin film that separates the surfaces, preventing direct metal-to-metal contact and thus reducing friction and heat generation. Selection of components. The process begins with selecting the appropriate type of bearing for the application. Bearings come in various designs, such as ball bearings, roller bearings, and plain bearings, each suited for specific loads and operating conditions. Preparation of bearing housing. The bearing housing is the component that encases the bearing and provides support. It is important to ensure that the housing is clean, properly aligned, and free from defects before assembly. Mounting the bearing. The bearing is carefully placed within the housing, ensuring proper orientation and alignment. Precision is crucial at this stage to prevent misalignment, which can lead to premature wear and failure. Applying lubrication. Lubricating oil is introduced into the bearing housing. The amount and type of oil used depend on factors like load, speed, and temperature. The oil should be of the right viscosity to form an effective lubricating film. Sealing. Proper sealing is essential to retain the lubricating oil within the bearing housing and prevent contaminants from entering. Seals or gaskets are installed to maintain an optimal environment for lubrication. Securing the housing. The bearing housing is securely fastened to the surrounding machinery or structure. This step ensures stability and prevents unwanted movement that could affect the bearing's performance. Testing and monitoring. Once the oil lubrication bearing assembly is complete, it undergoes rigorous testing to verify its performance under various conditions. This may involve running the machinery at different speeds and loads while monitoring temperature, vibration, and other parameters. Maintenance. Regular maintenance is crucial to keep the bearing assembly functioning optimally. This includes monitoring oil levels, changing lubricating oil when necessary, and inspecting the assembly for signs of wear or damage. The Darlington generator stator, a remarkable feat of engineering, recently embarked on a momentous journey from the GE factory in Wrocław, Poland. Destined for Canada, this event marks a significant milestone in the global energy landscape, as it underscores GE Power's prowess as a preeminent energy solutions provider operating on a truly global scale. GE Power, renowned as a world energy leader, stands at the forefront of the energy industry by delivering a comprehensive spectrum of cutting-edge equipment, solutions, and services spanning the entire energy value chain. With a sprawling presence across over 180 countries, the company's technological innovations contribute to the generation, transmission, and consumption of electricity on a global scale. The Darlington generator stator, a remarkable feat of engineering, recently embarked on a momentous. The Darlington generator stator represents the embodiment of GE Power's commitment to pushing the boundaries of engineering excellence. As it begins its transcontinental voyage from Poland to Canada, it symbolizes the critical role GE plays in powering the world. This stator, a vital component in power generation, exemplifies the intricate synergy of advanced technology and meticulous craftsmanship. GE Power's influence is staggering. It's responsible for generating 1/3 of the world's electricity, enabling the functioning of 90% of power transmission utilities worldwide, and managing an astonishing 40% of the globe's energy through its sophisticated software solutions. In August 2018, a critical incident occurred at Unit 2 of a hydroelectric facility, causing smoke and severe damage to the generator's core. The urgency to repair the unit and minimize revenue losses prompted a comprehensive assessment by a technical team to identify the root cause of the failure and devise an effective solution. A breakthrough emerged with the introduction of Cora, a novel technology involving state-of-the-art bars that had not been utilized for this particular machine before. This innovation opened doors to new possibilities for enhancing the generator's performance. The proposal to the customer was compelling: a commitment to restore the machine to operational status within 78 days, accompanied by a 5-year warranty. Safety emerged as a paramount concern, especially given the project's location within a tunnel. The company, being safety certified, ensured rigorous training for the entire team, both on-site and in the production line, to align with the customer's safety requirements. The restoration endeavor was no small feat, with around 50 personnel working on-site and an additional 65 engaged in the coil factory. The task involved 24/7 coordination across different locations. The goal was not just to repair, but to enhance the generator's output. Redesigning the entire coil setup was imperative to achieve a 12% increase in power output. The timeline was meticulously planned. The first batch of bars needed to arrive on-site by the 30th day. In 8 separate shipments, the bottom bars were manufactured and sent. Installation commenced as soon as the first shipment arrived, ensuring a synchronized workflow. This simultaneous progress was maintained throughout the project, ensuring optimal efficiency. Originally focused on rewinding the stator with 450 new bars and core restacking for the first 3 segments, the project scope expanded as the rotor's issues were discovered. The rotor, identified as the root cause of failure, had problems including interval jumper issues, fan imbalance, and loose-fitting water pins. Addressing these, Korean suppliers manufactured new pins and modified the rotor accordingly. Quality assurance was a primary concern. The company emphasized stringent testing processes to ensure the highest standards were met. The meticulous testing regimen was pivotal in providing assurance to the customer and setting a benchmark for post-project performance. Looking forward, the successful completion of this project positioned CORAL for an improved standing in the after-sales service market. Investment in cutting-edge robotic machinery and a new factory underscored the commitment to quality and efficiency. With a strong foothold in the domestic market, the company set its sights on the global arena, aligning with an aggressive expansion strategy. The restoration and uprating of the 5.5 MVA hydro generator showcased the convergence of technology, teamwork, and innovation. From swift problem analysis and safety-conscious execution to redesigning for enhanced output, the project not only revived a critical asset, but also projected CORAL as a contender in the global market. Water Power Volk AG, WKV, is a distinguished manufacturer of turbines and generators, steeped in a rich tradition of craftsmanship and a steadfast commitment to quality. This commitment is seamlessly integrated with cutting-edge manufacturing technology, resulting in top-tier products designed to serve the energy needs of generations to come. The company's dedication to a sustainable energy economy underscores its recognition of the critical role renewable energy plays in the future. Among the plethora of renewable energy sources, hydropower stands out as an exceptional contender. In this realm, WKV has secured its position as a global frontrunner in producing small and medium hydropower systems. Operating under the banner of Made in Germany, the company's facility in Gutach shines as a beacon of innovation, boasting the distinction of being Europe's first heavy machinery factory to operate with near-energy autonomy and minimal carbon emissions. This accomplishment is further highlighted by the facility's hydropower installation, that not only powers its large-scale production, but also fuels heat pumps for space heating while exporting surplus energy back to the grid annually. As a medium-sized enterprise, WKV takes pride in its strong roots in Germany, recognizing its social responsibility to both present and future generations. The company's operations serve as a testament to the harmony between expertise and motivation. A workforce equipped with ongoing training and development ensures the long-term reliability and continuity that customers can rely upon. A multidisciplinary team of expert engineers, ranging from water management and civil engineering to mechanical engineering, electrical engineering, and control technology, spearheads the planning of hydropower plants. Their comprehensive knowledge spans every facet of the field, setting the stage for the company's pivotal role in advancing the harnessing of waterways. Integral to this effort is the company's in-house turbine testing facility, where meticulous research is conducted on turbine models. This rigorous testing regimen guarantees optimal flow results and maximum efficiency, a vital component in effective waterway utilization. WKV's prowess shines particularly brightly in its expansive lineup of turbine types. The company stands as the sole manufacturer, offering a quartet of turbine variations: Francis, Kaplan, Pelton, and cross-flow turbines. This diversity empowers WKV to leverage the unique characteristics of various watercourses and cater to a wide spectrum of requirements. ranging from smaller cross-flow systems of around 300 kilowatts to substantial Francis and Kaplan turbines boasting capacities of up to 25 megawatts. WKV's comprehensive offerings ensure a customized approach to each project. The company's self-reliance extends to its supply chain, enabling flexibility and short project turnaround times. Equipped with state-of-the-art machining equipment, WKV's emphasis on precision underpins the high quality of its products. Each component is meticulously sealed and coated, guaranteeing longevity while adhering to the visual perfection that defines the company's legacy. WKV's commitment to excellence also shines through in its approach to assembly. Turbine systems are pre-assembled at the factory, streamlining on-site installation for optimal efficiency. Control and automation systems, developed and manufactured in-house, undergo rigorous functional testing alongside turbines before deployment. Going the extra mile, the company can also design and supply a range of additional systems, including low, medium, and high-voltage systems, transformers, crane systems, and emergency power generators, further consolidating WKV's role as an end-to-end provider. One of WKV's crowning achievements lies in its capacity to independently manufacture synchronous generators within its shared facility. This rarity in the industry is underpinned by decades of experience among the company's engineers, who guide the production process from coil fabrication to the testing of high-efficiency generators. The use of premium materials and the expertise of skilled professionals yield machinery that's both remarkably durable and highly reliable. Specialized rotor winding machines, tailored to WKV's specifications, facilitate the creation of motors engineered to withstand the most demanding conditions. Ensuring the mechanical and electrical robustness of its generators, WKV operates one of Europe's most advanced impregnation facilities. Here, rotors and stator cores undergo treatments that optimize their mechanical and electrical strength. The culmination of this process is the meticulous testing each generator undergoes in the company's dedicated testing field, resulting in comprehensive test reports for each machine. Customers are even afforded the opportunity to accompany their generators during trial runs, validating their performance and ensuring their suitability for deployment anywhere across the globe. The emphasis on safe delivery is evident in WKV's operation of its own specialized packaging facility. The 14RT Flex 96C is not just an engine, it's a marvel of precision and performance. With a focus on both power and environmental responsibility, it offers an impressive output that defies conventional norms. Boasting a power output of insert power output, this colossal engine is the go-to choice for industries demanding unparalleled power, such as marine propulsion for large vessels. What sets the 14RT Flex 96C apart is its revolutionary technology, employing a flexible camshaft system that allows for optimal combustion control. This technology enables the engine to adapt to varying load requirements, ensuring fuel efficiency and emissions reduction at all times. This adaptability grants it an advantage over its predecessors, making it a trailblazer in the era of sustainable energy solutions. Moreover, the engineering behind the 14RT Flex 96C focuses on minimizing environmental impact. Its advanced design not only maximizes power output, but also prioritizes fuel efficiency, leading to decreased fuel consumption and subsequently reduced emissions. In a world increasingly concerned about carbon footprints, this engine stands as a beacon of progress. The Julius Nyerere hydropower project, located on the Rufiji River in the southeastern part of the United Republic of Tanzania, is a significant endeavor aimed at providing both power generation and irrigation flow to the region. This ambitious project has its roots tracing back to the 1960s, when the Tanzanian government initially conceived the idea. Upon completion, the dam is poised to become the fourth largest in Africa, the ninth largest globally, and a pivotal power station for East Africa, with a projected reservoir spanning 100 kilometers in length and covering an area of 1,200 square kilometers, containing a colossal 34 billion cubic meters of water. The hydropower project holds immense potential to meet the region's energy and water management needs. The project's strategic location, approximately 350 kilometers from the bustling coastal city of Dar es Salaam, positions it advantageously for meeting both local and regional power demands. The Rufiji River, the longest river in Tanzania, with its expansive catchment area of 184,000 square kilometers, forms the foundation for this hydropower endeavor. The controlled catchment area immediately upstream of the dam site spans 158,000 square kilometers. This expansive catchment area facilitates the accumulation of considerable water resources, ensuring a stable flow for power generation and irrigation, even during varying weather conditions. Central to the project's architecture is the roller-compacted concrete (RCC) gravity dam, a formidable structure designed to harness the power of the Rufiji River. The dam's imposing 134-meter height lends it prominence on the landscape, while its arched design imbues it with both strength and elegance. The reservoir it creates not only encompasses a vast expanse, but also provides a means of regulating the river's flow, ensuring optimal conditions for power generation and irrigation downstream. This dam, in compliance with safety standards outlined by the U.S. Army Corps of Engineers, is classified as a large project, necessitating stringent safety and flood control measures. The dam's operational layout further comprises essential components such as the main spillway integrated into the main dam, along with 4 saddle dams situated on the right bank. These features play a crucial role in managing the reservoir's water levels and controlling the flow of water for various purposes. An emergency spillway located on Saddle Dam No. 1 enhances the project's resilience by providing an alternative outlet for water during unforeseen scenarios. Additionally, the inclusion of power waterways and a ground powerhouse on the right bank of the river establishes the infrastructure necessary for converting the stored water's potential energy into electrical power. The anticipated output of the Julius Nyerere hydropower project is staggering, with a total installed capacity of 2,115 megawatts (MW) and an annual power generation of 6,307 gigawatt-hours (GWh). This substantial capacity is poised to play a transformative role in Tanzania's energy landscape, contributing to the country's economic growth and sustainable development. Notably, the power station's annual output of 5,920 gigawatt-hours is expected to alleviate power shortages and meet the rising electricity demand within the region, benefiting both urban centers and rural communities. Ownership and management of the hydropower project are vested in the Tanzania Electric Supply Company, TANESCO, a government-owned entity. This arrangement underscores the project's strategic significance for national development and energy sovereignty. As the largest power station in East Africa upon completion, the Julius Nyerere hydropower project will not only provide a significant boost to Tanzania's energy capacity, but will also position the country as a regional energy hub. The manufacturing process of the Julius Nyerere hydropower project involves the meticulous construction of a monumental RCC gravity dam, supported by a network of spillways, saddle dams, power waterways, and a powerhouse. The project's colossal scale and strategic location harness the potential of the Rufiji River, providing both power generation and irrigation flow to a region poised for growth. With Tanzania's commitment to realizing this ambitious venture, the Julius Nyerere hydropower project is set to reshape the energy landscape of East Africa, fostering economic development and securing energy access for generations to come. The manufacturing process of the Julius Nyerere hydropower project, also known as the Stiegler's Gorge hydropower project, is a complex and ambitious undertaking that aims to provide a substantial increase in Tanzania's electricity generation capacity. The project involves the construction of a massive dam and hydropower plant in the Stiegler's Gorge area, with the goal of addressing the country's electricity shortages, supporting industrialization, and fostering economic growth. The project underwent a significant phase of redesign and planning, resulting in a new design unveiled in 2018. This new design features a dam wall that is 131 meters high and spans 700 meters in width. The scale of this dam is set to make it Africa's largest in terms of installed capacity upon completion, surpassing notable counterparts like Egypt's Aswan High Dam, Mozambique's Cahora Bottom. With an impressive installed capacity of 2,115 megawatts, the Julius Nyerere hydropower project is poised to exceed Tanzania's current peak electricity demand, which reached 1,051.27 megawatts in February 2017. This substantial increase in electricity generation is crucial for the country's industrialization and electrification efforts. It aims to alleviate the regular electricity crises that Tanzania faces, particularly during dry seasons and below-average rainfall years, which have significant social and economic repercussions. The power shortages often result in load shedding, leading to notable economic losses, estimated to be between 5 to 7% of Tanzania's GDP during the 2014-2015 period. The groundwork for the construction process was set in motion by Tanzanian President Magufuli, who directed TANESCO, Tanzania Electric Supply Company, to prepare the construction site. Contracts were awarded to clear the construction area, create suitable roads for heavy vehicles, and establish power and water infrastructure. The process also involved granting logging rights in the reservoir area, potentially generating substantial revenue for the project. The manufacturing components of the project involve collaborative efforts between various entities. The civil engineering works were entrusted to Arab contractors, a state-owned Egyptian firm, while El Saudi Electric took charge of installing the electromechanical equipment, including turbines, generators, and transmission lines. These contracts were signed with Taines CO, the state-owned energy utility company. Financing for the project comes from various sources. While the government announced that it would be funded through Tanzania's national budget, additional financial support was necessary. Despite the World Bank and other financiers declining to back the project, El Saudi Electric secured a loan of $500 million from the African Export-Import Bank. This loan is fortified by guarantees from the United Bank for Africa and CRDB Bank. The intention is to repay this loan through the project's contractual obligations. Stretching across the Jura Mountains between Basel and Egerkingen, the 3.2-kilometer-long Belchen Tunnel stands as an engineering marvel and a testament to human ingenuity in overcoming geological challenges. The Jura Mountains are characterized by the prevalence of gypsum cupar, a rock that swells significantly upon contact with water, posing unique complications for tunnel construction and stability. As a result, the need for renovating the existing double-track tunnels from the 1970s arose, leading to the creation of the Belchen Tunnel project. Central to the success of this endeavor is the use of a state-of-the-art tunnel boring machine and meticulous construction techniques, demonstrating the capability to overcome even the most demanding geological circumstances. To address the looming renovation of the A2 motorway tunnel that is now 50 years old, the construction company Martin faced the challenge head-on by designing a replacement tunnel adjacent to the existing one. This strategic decision aimed to minimize disruptions to traffic flow while allowing for the comprehensive renovation of the aging tunnel. The venture encountered a unique hurdle due to the presence of gypsum cupar in the mountain's composition, which can rapidly expand upon contact with water. This necessitated the rapid concreting of a substantial inner structure behind the excavation to prevent complications during construction. The tunnel boring machine designed by Herenicht and Marty Technic became the cornerstone of the Belchen Tunnel project. This remarkable machine operates by excavating the tunnel along its 75-meter length, placing segments, sealing, and completing the concrete lining in an integrated process. A distinctive feature is the 14-meter diameter cutting head, fitted with specialized rollers that chip away stone splinters as they rotate. The arrangement of these rollers is optimized for the specific geology of the Belchen Tunnel, and injection openings behind the cutting wheel stabilize and inject material into the rock. With up to 2,000 tons of pressure, the machine advances while simultaneously filling the gap between the tunnel and the rock with rapid hardening mortar. The tunnel boring process involves meticulous precision and coordination. Every 2 meters, the machine halts to construct a tunnel ring consisting of 7 segments, employing the Thuringian method to secure the tunnel directly behind the press by closing the first ring. Each segment is completed in approximately 25 minutes, with the components manufactured using high-strength steel fiber-reinforced concrete. The segments undergo further reinforcement in a 55-degree hot oven, ensuring their durability and strength. The sequencing of these segments determines the tunnel's curvature progression, allowing for 13 different positions and curves in the tunnel's development. Simultaneously, the process maintains strict control over air quality within the workspace. At the machine's end, a conveyor belt transports excavated material away, continuously extending as the machine advances. Given the risk of rock swelling, Martin undertakes the construction of an additional inner structure in the tunnel shortly after initial excavation, all the while ensuring the continuous operation of the tunnel boring machine. The tunneling endeavor extends to the construction of the tunnel floor, which involves an intricate sealing process to ensure water tightness. Foil sheets with remarkable pressure and abrasion resistance are applied, transforming the tunnel into a waterproof structure. Subsequent concreting is carried out under challenging conditions, with concrete being pumped in using specialized equipment. This phase involves complex maneuvering due to varying wall thicknesses and reinforcement structures. Notably, the concrete is produced on-site in a mobile concrete plant, adding to the project's self-sufficiency. The completion of the intermediate sealing marks a significant milestone in the tunnel's construction, serving as both a structural element and a channel for ventilation and escape. The entire process, from cutting through the mountain's rock to the finalization of tunnel components, showcases the integration of innovation, precision, and expertise. Despite the geological challenges posed by the presence of gypsum cupar, the Belchen Tunnel project stands as a testament to human capabilities in engineering and construction. Through the strategic use of cutting-edge technology and meticulous techniques, the tunneling endeavor exemplifies the capacity to triumph over even the most formidable geological obstacles. Covanta's Dublin Waste-to-Energy facility, situated in the heart of Dublin Port, Ireland, stands as a testament to modern engineering and sustainable waste management practices. The year 2017 marked a significant milestone for this groundbreaking project, as it completed its construction and underwent final performance demonstration tests, marking the transition to full operational status. This state-of-the-art facility, designed to convert solid waste into electricity through innovative waste-to-energy technology, not only addresses the issue of waste management, but also contributes to the generation of clean energy. The Covanta Dublin Waste-to-Energy facility, located at Poolbeg in Dublin Port, boasts an impressive operational capacity. The facility's machinery can process a staggering 1,800 metric tons of solid waste per day, showcasing the sheer scale of its waste management capabilities. As a result of its daily operations, the facility contributes to the generation of an impressive 60 megawatts of electricity. signifying a significant step towards a greener and more sustainable energy future for Ireland. The construction of the Covanta Dublin facility was no small feat. The project involved the implementation of advanced construction techniques and materials to ensure its success. A remarkable feature of the construction process was the installation of an astounding 4,350 piles with a combined length extending over 69 kilometers. The use of concrete slip forming, a continuous pouring technique, played a pivotal role in the construction process. This method allowed for the pouring of a substantial concrete volume, amounting to 60,000 cubic meters, which is equivalent to approximately 7,500 truckloads of concrete. Impressively, the construction team managed to pour a maximum of 3,200 cubic meters of concrete in a single day, demonstrating their efficiency and expertise. Reinforcing the structure was a key element of the construction process, with a staggering 6,450 tons of reinforcing steel utilized. The facility's formidable structure comprised 8,800 tons of process and building steel, highlighting the engineering precision that went into creating a durable and reliable waste-to-energy plant. To achieve optimal operational performance, each of the two operational lines featured 2,304 filter bags, collectively ensuring effective filtration throughout the waste-to-energy conversion process. Environmental considerations were at the forefront of the facility's design and construction. Independent testing confirmed that the facility's emissions of dioxins and furans were an impressive 98.14% below the stipulated license limits. Similarly, total particulate matter emissions were significantly reduced, measuring 96.37% below license limits. These findings underscore the commitment to adhering to stringent environmental standards and minimizing the facility's impact on the surrounding ecosystem. The Covanta Dublin waste-to-energy facility's capabilities extend beyond waste management and energy generation. With a permitted capacity to process 600,000 tons of residual municipal solid waste, MSW per annum, the facility plays a crucial role in waste reduction and resource recovery. The electricity generated by the facility can power approximately 80,000 homes, while its district heating provision benefits an additional 50,000 homes, contributing to the local community's energy needs. The immense effort invested in the construction and operation of the Covanta Dublin facility is reflected in the cumulative man-hours of labor dedicated to the project. An astonishing 3.8 million man-hours were expended to bring the facility to its operational status, a testament to the dedication and skill of the workforce involved. The inaugural burn on June 1, 2017, marked a significant milestone in the facility's journey, symbolizing the culmination of years of planning, design, and construction efforts. With its efficient waste-to-energy conversion process, rigorous environmental standards, and substantial energy generation capabilities, the Covanta Dublin waste-to-energy facility stands as a pioneering example of sustainable waste management and clean energy production, shaping the path toward a more environmentally conscious future for Ireland. The Covanta Dublin project underwent a transformative phase on December 14, when it successfully completed a comprehensive refinancing of its original capital structure. The outcome was an extension of maturities and a reduction in costs, significantly benefiting the project's financial landscape. Two key elements of this refinancing were the acquisition of a new €396 million senior loan, due in 2032 at a favorable rate of 3.1%, and a new €50 million second lien junior loan, also due in 2032 at a rate of 5.2%. These financial maneuvers allowed for the repayment of all existing senior and junior debt, including the 13.50% convertible preferred instrument held by BlackRock. A noteworthy aspect of this debt issuance is its non-recourse nature to Covanta and the joint venture, JV. underscoring the strategic financial planning behind the refinancing. This endeavor not only strengthened the project's financial position, but also highlighted Covanta's commitment to optimal capital utilization and long-term sustainability. Partnerships played a pivotal role in the project's evolution, with the Green Investment Group, GIG, becoming a prominent partner. GIG's investment of €136 million secured them a 50% ownership stake in the Dublin project through the JV. This step marked the inception of a partnership that aimed to combine Covanta and GIG's UK development pipelines. The combined pipeline featured a total of 6 projects with a cumulative annual waste processing capacity of 2 million tons. Situated strategically across the UK's attractive waste markets, these projects held significant promise for both entities. The valuation of the Dublin project was a testament to its status as a premier world-class asset. The purchase price indicated an enterprise value of approximately €700 million, which was around 13 times the projected full-year adjusted EBITDA of the project company. This valuation, well above the development and construction costs, reflected the asset's exceptional market position and potential. The partnership with GIG was not just a financial arrangement, it represented Covanta's strategic approach to resource allocation and growth. By recycling a substantial portion of its invested capital from the Dublin project, Covanta could reinvest in its UK pipeline. This forward-thinking strategy enabled Covanta to retain a 50% equity stake in the Dublin project, thus ensuring its continued involvement as the operations and maintenance (O&M) service provider.